Right, last time we started talking about dependent motion and we solved like 2 examples. But before, I'm gonna solve another 1 or 2 examples. I'm not sure if you guys checked the notes. There's some examples there. I believe the dependent motion is one of the most easiest problems if you get the idea. Next, on Thursday, we are gonna have our second quiz. It's gonna be on curved linear motion and independent motion, okay? So maybe you study the tangent normal, polar coordinate system, and also the independent motion. So you might expect the questions in these topics. Right, the second thing for the grading, we have there was some difficulty in adding the TA to the Canvas course. So right now I believe we solved the issue. Once he gets in, he's gonna grade the homeworks and the quizzes right away. Okay? But if you have any questions, send me an email with your question. If you wanna meet me, we can do Zoom meeting and meet together. And after the class, I usually be in my office. I have some meetings. That's why I ask you maybe to send me an email to check that I have a spot for you. But if you want to stop by, that's fine. If you want to send me an email and we do a Zoom meeting, that's also fine. Okay. All right. So I'm gonna solve another 2 examples just to make sure that the concept of dependent motion is okay with you. Okay. So first, in solving these problems, you need to make sure how many ropes or how many chords you have. So here in this problem, this is my fixed surface, and I have mass B here, and this mass B is allowed to move in the y-axis like this, and it's connected to 2 chords. This is the verse 1, and this verse 1 has pulley here, and this one is connected to a center of another one here. I draw them with different colors, or it's only one color, and then I have these are fixed pulleys to a fixed surface, but this one is a moving one. Okay. And this is our cord. It's like this, connected that way. Start from here and goes all the way around, then comes here and all the way around, then comes here and all the way around until you have a mass A here. Okay, so it's only one cord. And I told you in this problem that the body B is moving upward with VB equal to 6 feet per second. Okay, let me ask you, if body B is moving upward, what do you think about body A? Is it going upward or downward? Downward, right? Because this cord is going to go up and all the other cords are going to go down. All right, so how to solve this problem? I told you that we only have one constant in this problem. The length of this cord is constant. It's not extending, it's not shrinking, it's the same. And there's some moving parts in this cord. And we said that we need first to find a fixed axis, like this is the fixed axis, and then start looking for the moving point. So at this point, I want to tell you something. The velocity of this pulley is the same velocity as B, because all this party either goes up together or goes down together as a one piece. Okay? Like this one is restricted, like this cord cannot go up and this one is not moving. They either move together or goes down together. So I can say I'm only interested here, like this length, let's say this is YB. Why did I do that? Why didn't I go all the way to the length there? Because I know that this piece and this piece are gonna be always there, are not gonna be changing in length. But this pulley, if this moves down, these two are gonna get less and gonna go up. But this part is not gonna change. This length will never change because there's nothing is pulling it up and down. So it's always these 2 pieces. Okay, what else is it changing? This length, YA. This is the two lenses that they are changing, okay? This is moving down, this lens is elongating, and this one is getting short. So all this system is gonna go up, but this is gonna be less. Oh, sorry, this is gonna be constant. All right, so let's see what are the lenses that we have here that are constant. I have here 1 YB, 2 YB, 3 YB. I have 3 YBs, 1, 2, 3. So I have 3 YB. That is the 3 lenses that are changing. And I have 1 YA are equal to constant. If you want to include the whole length of the cord, you can. Like you can say, as I said last time, you can include this. You can include this piece, let's name it L1, and you can include this lens piece L2, L3, this piece, and L4. And you can put them here in this equation and say that L1 plus YB plus L2 plus YB plus L3 plus YB plus L4 plus YA is equal to the length of the cord. But all these lenses are constant, like L1, L2, L3, L4 is constant. It's not gonna benefit me when I take dt of this equation, because they all are gonna be 0 because they are constant. I'm only interested in the variable lenses. So rather than saying all these lenses is equal to the L of the cord, I'm saying that the two variable lenses are always equal to constant, because if this is got decreased, it's gonna give more length to this. So this plus this is gonna be equal to constant. All right, so I have here 3 VB plus VA is gonna be equal to 0. I already know what is the value of VB, so VA is gonna be equal to negative 3 VB. And by the way, you tell me, I assume that YB is going down, and this is my positive, and here the value that is given, it's VB going up 6 feet. So you have to put VB with negative. So this is gonna be negative 3 multiplied by negative 6. This is gonna give you 18 foot per second. That means if B is going up with 6 feet per second, A is gonna go down with 18 feet per second, and it's positive and in the same direction of A. So be careful with the directions. Does anybody have any question?
Why is it negative 3?
Okay, because YB I assumed it's negative, it's going down. YB measured from here to here, and the velocity of B is going up in the opposite direction of YB that is assumed. If you want to keep it positive, you have to assume that YB is going up and YA is gonna go up. That's my assumption. Okay. All right, so let's solve one that has 2 chords. All right, so let's see here. I have this. So I have here 2 chords. The first one, I'm gonna make it red. It is attached to this ceiling and goes all the way around to all the way around to the center of this pulley, and that's the first lens. The second lens, or the second cord, is something also attached from the ceiling like this and goes all the way around. Move this too. And goes all the way around like here. Attach it to the ceiling. And then there is a weight A, and there is weight B here. I told you in this problem that the velocity VV is going up. By the way, the velocity of V is the same velocity as the bully. Why? Because they are attached to a constant length of a constant length cord. So they either move together or goes down together. They are not like here. So, okay, so VB is 6 feet per second. So I have VB 6 feet per second and going up. All right, so what I'm asking here, what is the velocity of A? Right, so let's look at this problem. So if VB is going up, how about VA? What is gonna happen to VA? It's gonna go down or go up? This one is going up, that means all these chords are going up, so that means that A is going down. That's like intuition. All right, so you guys tell me, how many equations do I have in this problem? Here I only have one equation because it's only one chord that is constant. Now I have two equations because I have this one and this one. This chord is constant and this chord is constant, okay? All right. Let's first find what is the fixed surface that I want to relate the distance to. Can you guys tell me where can I put my fixed distance length? You can put it here, but I would rather put it here. Right? And then I can measure the distance to this pulley. And I'm gonna call this YB. And I'm gonna measure also the distance to this pulley. I'm gonna call it YC. And the distance to this part, I'm gonna call it YA. That's the moving part. I have this can move up and down. I have this can move up and down. And this weight A can move and down. You're gonna say, but B also is moving up and down. Since I already included this pulley, this B is the same velocity as this. So basically I can say that the velocity of this is the same as the velocity of this. How about you guys tell me what equations do I have here? First, give me an equation of the red chord.
YB plus
Yeah, good.
YB minus
Excellent. YB minus YC. YB, this is the red part here, and this part, the red one, is going to be YB minus YC. All right, that's the first equation, and all this is going to be equal to constant. So 2YB minus YC equal to constant. I got my first equation. How about the second equation? The green chord. What is the length of the green chord? 2YC, excellent. I have 1C and YC plus YA, excellent. And all this is equal to constant. This part and this part and this part are equal to constant. So since you have the y's, you can get ddt for both equations and get the velocity equation. So basically, I'm gonna put the equations here so that you guys can see. You guys tell me, what is the equation of the velocity is gonna be? If you take ddt of this, it's gonna be 2vb minus vc equal to 0. dy dt is the v. The constant of dt is gonna be 0. All right, and then the second equation, 2vc plus va is gonna be equal to 0. What I have here, I have vb. So I can substitute in this equation, and this equation is gonna give me that vc is equal to 2vb, and this is 2 by 6. And this is going to be 12 feet per second. So if B is going up, I have VB should be negative. So why? Because VB is 6 going up and YB is going, like, direction is down. So this should be negative and this should be negative 12. And that's how I use my engineering sense to know that my answer is not right. Because when I look at this problem, if this is going up, this thing should be going down, so it's gonna be positive. It's a little bit tricky, this part. Okay, so this is negative 12 feet per second. No, sorry, it's gonna go up because it's negative. All right, so how about A? A, I have already VC is negative 12, so I have V8 is equal to negative 2 VC, and this is gonna be negative 2 multiplied by already negative 12. This is gonna give us 24 feet per second. And it's positive, that means it's going down, so everything should be right. Okay? We'll just put these equations rather than putting them down and put them up so that you all can see the answer. So already I got VA, which is requested in this problem. All right, so there's another problem that you guys can start solving. I'm just like giving you an example of how the problems, they all look like this. Try to look at the moving parts. Sometimes it's a little bit tricky, but just to track the lenses and also pick the right coordinate, the right fixed axis. Because if you pick one, like let's say that you picked something this up there, you have to assume some constant. Like you have to say that this is constant and then start measuring. So try to pick an axis that makes sense and it's much easier to deal with. This is actually examples from the textbook. So if you go to the textbook, it's gonna have a lot of explanation. With this, we finished chapter 12. There's one sub-chapter about the relative velocity. I'm not gonna get into this sub-chapter. I'm gonna skip it because down the road there's stuff that is not in the textbook that we need to explain about structural dynamics and fluid dynamics. So we have to skip some topics about dynamics that might not be that much important for you. Everything is important, but not right now. And do something else that is important down the road, okay? So I'm gonna skip the relative velocity part, and I believe it's, I can upload if you guys, I believe it's a chapter 1210. That's the chapter that is not included, the one related to relative velocity, okay? And now we are gonna talk about chapter 13, which is the force and acceleration, particle kinetics. All right, so in the first 6 chapters, we have been talking about the movements of bodies, and the movement of these bodies includes that we need to know how we can describe the position, how we can describe the velocity, how we can describe the acceleration. And actually what I was doing, I'm building some basis for this chapter, because you will not understand the force if you don't understand the acceleration. Because we all know about the Newton's second law, that the force is equal to mass multiplied by the acceleration, right? But we are gonna understand this concept as a little better here. So Newton's second law says it's an empirical equation which is verified, like the force F is equal to the mass multiplied by acceleration, and actually it's a vector, so the F vector, and there's a mass vector, the acceleration vector. So F is equal to ma, and this is an empirical equation which is verified experimentally by applying an unknown of balanced forces on a mass or a particle, and then measure the acceleration. So we will find that the force is proportional in the acceleration, and the proportionality factor is the mass. Okay, so it's a proven experiment. Okay, since the force and the acceleration are directly proportional, so that's why we can write this function that way. And sometimes we write this function in a different way. Like we say that the force is the time rate of exchange, of the linear momentum. The linear momentum is a quantity where you multiply the mass by the velocity of the particle. If you differentiated this quantity with respect to the time, it's going to give you the force. And actually that makes sense because usually the mass is constant, unless it's not constant. There's some applications when the mass is not constant, like let's say that you have a big rock is sliding from a mountain. When it slides, keep getting broken and keep getting smaller, so it's losing some mass. So the mass is losing, it has a function over time. So that's why we need to include the mass inside. But if it's constant, you can take the mass outside of this equation and you will end up with dv/dt, which is actually the acceleration. The time rate of change of the velocity is the acceleration. So that's the one way to do it. So it says that Newton's second law is not valid for high-speed particles that approach at the speed of the light. So if you approach the speed of the light, like things that happens in the space, this is not applied. And also Newton's second law is not valid for particles that are at the size of the atoms, like when it comes to chemical stuff and very, very small sizes, this also is not valid, okay? All right, so, but before I start this, I want to talk a little bit about the Newton's law of gravitational attraction. So what is the Newton's law of gravitational attraction? So Newton's find out that any bodies, they always have attraction. Like my body and your body, there is always attraction between the masses. But the thing is, we don't attract each other because our masses are small. But if our masses are big, we do attraction. Like the mass of the Earth and your mass. The mass of the Earth is really big. That's why you can't leave the Earth. That's why you're always attracted to the Earth. Like you cannot leave it. If you go up and you do a free fall, you are gonna go down to the Earth. Okay, so this rule is, it says that the attraction force F between two masses is equal to the universal constant of gravitation, G. It's a constant multiplied by mass m1 and the mass m2 over r squared, the distance between these two masses. Okay, so G, the universal constant of gravitation, is equal to 66.73 multiplied by 10 to the power 24. Negative 12. And this quantity is meter cubed per kilogram per second. Okay, that's the gravitational constant, the universal constant of gravitation, G. How about M1 and M2? All right, let's take this as an application for the Earth. Let's say that this is the Earth. It has radius R, and this R actually is known. The radius of the Earth is 6.378 multiplied by 10 to the power 6 meter. Okay, that's the radius of the Earth. And the mass of the Earth has a mass of m Earth, and this mass is equal to 5.97 multiplied by 10 to the power 24. Okay, so right now we have the radius, we have the mass of the Earth, and let's say you're like on top of a building. Or not you jumping, like you throwing a mass from this building. Okay? And this mass is at a height of 30 meters or 100 meters. Okay, like let's say this mass from here to here is delta, and this delta is 30 meters. Technically, I can assume this delta is 0. Why? If I want to find the center of the mass that you are throwing from the top of the building, and to the center of the earth. The center of the earth is 6.378 to the power 6. This distance, 30 meter or 100 meter or 1,000 meter, is nothing gonna show up here. There's gonna be one number here. Actually, it's gonna be, I don't know, like 6 zeros. It's not gonna show up. So basically, your body that you are throwing is at distance 0 from the earth. So basically, the distance between your body and here is still r. Okay? Unless you are throwing this something from the space. Okay? And your r is much bigger. Okay, let's say I have a body here, and I want to find what is the force between both of them. So basically, I can write this equation as the force actually here is called the weight. What I'm trying to find right now is the weight of this body, W. And that weight is going to be equal, or the force between them, or the attraction force between them, is going to be equal to the universal constant of gravitation multiplied by the mass of the earth, multiplied by the mass of the body that you have, over the distance between them, r squared, the distance between them is squared. So these two together we call this the gravity constant, like g multiplied by the mass of the earth over the radius of the earth square, that is g. So basically this is going to be equal to m multiplied by g. If you take the gravitational constant that I wrote here and multiply it by the mass of the earth, which is over there, and divide them over r squared, is going to give you g is 9.81 meter per second squared. Like, let's say in an example, I give you, yeah.
What did you make r equal to there?
Here?
Yeah, what is it equal to?
6.378 multiplied by 10 to the power 6 meter.
Okay.
All right. So if I give you an example, Neptune, I give you the mass of the planet Neptune, and I give you the radius of Neptune, and you already know the gravitational constant. If you multiply them together, you can get what is the gravitational acceleration at Neptune, okay, which is 11 or something. Okay, so in any planet or anything, you can do the same thing. You can find the attraction force between two bodies, the Earth and Neptune. Right now, you have the mass of the Earth and the mass of the Neptune. And what is the radius between them? The radius between Neptune and Earth is huge, right? It's very far away. So actually, this number is going to be huge. So you are dividing on a huge number. So basically, you are going to find a minimal amount of attraction between two far bodies from each other. As soon as they are close to each other, they are going to attract each other. Anyway, so we have F equal to mg, and that's what we call the weight of the body is equal to m multiplied by g, and then you can get the mass by dividing w over g. So be careful in problems. If I give you a problem and I'm saying that a body is has a weight of 10 Newton, that's W. And if you want to find the mass, you need to divide by G. And anything that is in kilograms, that means it's a mass. Okay? And anything that is Newton, that means it's W. How about if I told you a body that weighs 100 pounds or 150 pounds? Is that a mass or a weight? Pounds are always weight. If you want to get the mass, you have to divide by a number. I'm not sure if it's in the sheet or something, so that you can convert the pound to a mass. Do you guys know what is the mass from the pounds? It's called slug. You convert from pounds as a weight to a mass. There's a conversion to convert it to slug. Okay? All right, so let's see how we can use this in the force and acceleration. All right, so So just like I wrote here, like when we say particle kinetics, kinetics means relating forces to motion. Kinematics is that when we study the acceleration, the velocity, the position, so that's called kinematics. And we are studying particle kinetics. Particle is a non-rotating bodies with concurrent forces. Like, because we're gonna do some rigid body analysis. I don't know, maybe 1 or 2 months from now. But rigid bodies is different from particles because particles, all the forces are concurrent. Like they apply at the center of the mass of the particle. But if you have a rigid body, maybe you have a force here and a force here and a force here. So not all of them are in the CGN. So that's what distinguish particles from rigid bodies. We are going to study rigid bodies and we are going to study particles. But all what we are doing right now, chapter 12, 13, 14, 15, is all on particles. 16, we're going to take rigid bodies, okay? So, and here we can apply the rule, like if you have a bunch of forces like this, F1 and F2, so basically you need to find what is the equivalent of these forces, and then the equivalent of these forces is going to generate acceleration, and the mass multiplied by the acceleration is going to be equal to the F force, okay? All right, so so the Newton's second law is the summation of the force F is equal to MA, okay? So the thing is, this law can take different shapes. Like if you are dealing with Cartesian, the A is gonna have X component and Y component. If you're dealing with tangent normal, it's gonna have tangent component and normal component. If you're dealing with polar, it's gonna have R and theta component. So right now I'm gonna put the three of them, like, I didn't put it here, but let me say, it's gonna be equal to the mass multiplied by the acceleration. This can take two shapes. It's gonna be MAX and MAY, or MA tangent and MA normal, or MAR and MA theta, okay? So basically that's a chapter, that's a different chapter, that's a different chapter. Right now we are gonna focus on Cartesian or 2D Newtonian kinetics, like in X and Y, this one. So basically, if I give you any problem, try to find what is the acceleration in X direction, what is the acceleration in one direction, and solve the two directions separately, okay? All right, so, and I want to give you a steps how to solve problems. Like if I give you a problem, step number 1 is to identify the body. What do I mean by identify the body? Like, yeah.
Can you write a little larger on that?
Okay.
Screen? Thank you.
So identify the body. Like let's say I'm throwing, like you have, like let's say that you are shopping and you are in Walmart or something, or Target. You are having something and you throw it on the belt that is moving, okay? So, and you are studying this body, you are not studying the belt, okay? So that's why you have to choose the body, you have to identify, because you are saying the body is moving and the belt is moving. So which one I'm studying? So you are studying the body, so you have to take this body and isolate it and then identify what all the forces on this body. So first to choose the body. Number 2, you have to draw something called free body diagram. That's mandatory. If you didn't draw a free body diagram, I'm gonna tell you what it is, but you have to draw it because if you didn't draw, you are gonna lose at least, I don't know, like 10% or 15% of the points of the problem. And then the second thing is to draw something is called the free body diagram, and I didn't write it here, but you have to draw kinetics diagram. And number 3, you have to pick a coordinate system. Either X and Y, tangent normal, R and theta, because in the problem I'm not going to tell you what coordinate system that you should pick. Okay? Number 4 is to apply the Newton's second law, like to apply the summation of the force equal to the mass multiplied by the acceleration, which is here, and then you can pick x and y, tangent, normal, r, and theta. And then solve using common sense. Okay, that's the steps. But let's see how we do this in real problems. Like, let's say that you have a skier is gonna, like a skier like standing here, let's say this skier is something like this. And it's gonna ski down on a slope, and this slope is 40 degrees, okay? And I said that the skier starts at rest. At rest, that means S equals 0 and T equals 0, and also V is equal to 0, we know. And traveled 20 meter horizontal down. So, travel 20 meter down. So the final S was 20 meter. And the skier did this 20 meter in 2.58 seconds. So the time was 2.58 seconds. What is the kinetic friction coefficient? What is the kinetic friction coefficient? Right, so let's see this. First, what I told you is to draw something called a free body diagram, and on this free body diagram you have to put all the forces on the body. Okay, it didn't give you the weight of the skier. The weight of the skier should be given. Actually, it's a mass. The mass is 100 kilogram. I give you the mass of the skier. 100 kilogram. Okay. First, this is the free body diagram. Let's say I'm gonna draw the mass like this. Alright? You guys can tell me all the forces on the skier while he's skiing down. Normal force, right? Like if you are sitting like, okay, like if I have this water bottle on this surface, there's always normal force that makes this water bottle doesn't move. Okay? If I'm pushing something here, there's always a normal, like reaction force. There's always a reaction. So this skier is sitting on an inclined surface. Always the normal force is perpendicular to the surface that you are sitting in. Like if you are like this, it's gonna be like this. If you are like this, it's gonna be like this. So it's always perpendicular. So let's put first the normal force. What else? What other forces? Friction. Since she is moving down, so the friction is always opposite in the direction of the motion. If I know that it's moving down, and that's what it's saying in the problem, so always the friction is tangent to the surface, opposite to the direction of the motion, right? Okay, what other forces? That's the main force that I give you in the problem. And what is related to the gravity? The gravity is not a force, the gravity is an acceleration. Your weight is the one, so yeah, the weight is going down. And it's always in the gravity direction, like it's always going down like this, right? So that is the three main forces that acting on this body. That's why before you start any problem, you have to lay out all the forces on this problem. Maybe I give you this body as a spring. Like let's say I tweak this problem and I give you, for example, this is your body, and your body want to move down, and you attach this body with a spring like this. Your body want to move down, but what is restraining it? The spring, right? So you are going to have an extra force, F spring, going that way, right? What if I told you this body has a force like this, F? So there's an external force that you want to put on this body, F like this. So you need to lay out all the forces on your problem. First, you need to find out if there is a reaction, normal reaction, and that's, I believe, in most of all our problems, there is always normal reaction. Okay? There is friction. Until I told you this body's moving on a smooth plane. If I said smooth, that means there is no friction. Okay? And there's always the weight of the body. Okay. All right. That forces, that is called the free body diagram. By the way, all these are basics. Any problem, if you put this free body diagram in your head and starting writing equation and you didn't put this as a drawing, you are losing points. Okay? That's called free body diagram. What is the next step? That is all the forces on the body. Newton's second law is the sum of the forces equal mass multiplied by acceleration. This free body diagram gets you this, the forces, the left-hand side from the free body diagram. This side, we get it from something called kinetic diagram. I'm gonna do the same thing here with the body, like this. This is called kinetic diagram. In this kinetic diagram, we put the axes that we are choosing for this problem. Like, let's say, for example, I put the axes going up, I think, in this problem. I'm gonna put the axes here going down. You can do whatever you want. Like, let's say, I'm gonna assume the x-axis that way, and y-axis is that way. You can assume the x-axis going up, or actually you can assume the x-axis horizontal and vertical. But I did it in the same motion of the body. Why? Because I know this body has acceleration in this direction, right? The body's moving that way, so all the acceleration in that way. So what I want to do is, I want to have the acceleration here is MA. That's the direction of the acceleration. So what is in the kinetic body diagram? It's the axis and the direction of the acceleration. By the way, you can assume the direction of the acceleration in the other direction. You can assume it any, I don't know, right? I'm just assuming stuff, but I assume based on the common sense, on the engineering sense. I know this body's going down, and the gravity is down, so this body is always accelerating downward, not upward. So it means that way. All right, what if I put x, y axes, horizontal and vertical? Like I put x, here's y, and here's x. For sure, I know this body's moving down, right? This is the direction of MA. So you will end up with MAX and MAY. And you having two equations, and the two equations has the left side with numbers. What I did here, I did all the acceleration in the x direction, so there is no acceleration in the y direction. So when I build this equation, I'm gonna do two of them, and you are gonna see right now what I'm gonna do. All right, so what I'm gonna do right now, this equation, the summation of the forces equal to the mass multiplied by the acceleration. I'm gonna do one in the x, sum of the force. Let's name it in the x direction. I didn't write it here, but you can be organized. I didn't write it in my notes, but you can say in x direction. And here in y direction. Okay, in x direction, the sum of the forces in the x, right now, I don't have the vectors because I take the two components of the vectors to sum fx and sum fy. This is going to be equal to max, and this is going to be equal to may. So for sure, I know here all the acceleration is going to go down. There is no acceleration in y, so I know that ay is equal to 0. So the sum of fy is going to be equal to 0. So let's find what forces are in the y direction. Tell me. What of these forces are in the y direction? The normal. Is it positive or negative? Positive, because in the same direction of y. But if your y is going down, it's going to be negative. So I have n, and it's positive. What else in the y direction? The weight component in the y direction. So you guys know geometry, right? So this angle is 40 degrees. You guys want to know where it comes from? Do you all know? Like this angle and this angle is 90 degrees, and I know that this and this is 90 degrees, so this and this are equal. So this is 40 degrees. So what is the component in the y direction? Is the cosine or the sine component? The cosine component, because this is the cosine component and this is the sine component. And is it positive or negative? W is going down and Y is going up, so this is negative W cosine 40, right? Okay, and all this is equal to 0. Why? Because the if of friction is all in the x-axis. Alright, so right now I can get what is the normal is equal to. The normal is going to be equal to W, and W I know the mass, so this is going to be 100 multiplied by 9.81 multiplied by cosine 40. Do you guys have calculator to calculate this quantity? Because I didn't calculate it here. Anyway. Does anybody have a calculator? Is it? I'm solving this problem kind of a little bit different from here, but it's gonna be the same thing.
I got 751.49. 51.49.
751.49 is gonna be Newton, because kilograms, 1 Newton multiplied by acceleration, is gonna be Newton. Okay, let's take the x direction. What forces are in the x direction? The friction. All the friction is positive or negative? Negative, so I have negative F friction. How about, what is there other forces?
Sine of the weight.
The sign of the weight. So I have it positive, so plus W sine 40, and this is going to be equal to MAX. Why? Because I have an acceleration going down. The thing is, I don't know what is the AX value, okay? And the friction value is, you guys know what is the friction value? Okay, let me go back to the basics. I believe you guys did it in statics. Okay, so you guys, I believe in statics, you did something like this. You have a body, and this body is not moving, and this body has a weight W, right? You're gonna have normal force here, and there is F of friction here. If this body is something like this, this body doesn't move because of the friction. And you guys said that F of friction is function in the normal force and is equal to mu k multiplied by the normal force, right? Do you guys remember this rule? Did you take it anywhere?
Yep.
Okay. So the friction is always function in the normal force. How this is coming from? Like, let's say I have this body, and if I put just a little force here, so there's a little normal force, so if you push it, there is no much friction. But if I increase my load, so I increase the normal force, so if I try to push it, it's not gonna move fast. So the more that you increase the force, the more that you have normal reaction, the more friction you are gonna have, okay? So it's function in the normal force and the friction of the surface. Like, let's say I did the same thing on an ice, and I put this here and you pushed me, I'm gonna move. Why? Because the friction is very, very small when it comes to ice. So it's function in two things, the normal force and the friction of the surface. This, if the body is a static. If it's dynamic, it is the same thing. If the body is moving, it is also mu, and let's remove the K, and I'm gonna put static and dynamic. N. So there's a dynamic friction and there's a static friction. If the body is in a static, okay. So usually the dynamic friction is less than the static friction. Why? Because if the body is moving, there is less friction than if the body is still, okay? All right, so here, basically I can say that this is equal to N multiplied by mu friction, or mu dynamic, and that's actually what I'm asking for in the problem. Mu dynamic. Plus W, which is going to be M multiplied by G sine 40, and this all should be equal to M multiplied by AX. All right, let's see what I don't know here. I asked for, let's say, that's what I'm asking for. I know the normal force, I already got it here. I know the mass, but I don't know what is the AX, okay? If I know the AX, what is the acceleration, I'm gonna know what is the value of the friction. How can I know that? I give you some information in the problem. I give you information about the body started at rest, and cut distance 20 and time 2.58. I didn't give you this information for nothing. You are gonna do something with it. So let's see how we can use this information to find the acceleration. If you guys go back to the equations, and let me ask you, is that a constant acceleration problem or it's a variable acceleration? By sense, body is moving, sliding. So what is the only acceleration that this body have? You said it in a little bit when we started, the gravity, right? So the gravity is constant and it's taking this body down. The gravity is not changing over time. This body is doing a free fall. Nobody's pushing him, no motor is pushing him. He's moving with the gravity. If this body is wanna slide up, it's not gonna slide up because the gravity is taking him. Okay, so he's sliding down with the gravity and the gravity is always constant. So I can apply the constant gravity rules here on this problem. If you go back to the equations that we have from before, so you're gonna find out that we have an equation. Where is it? The equation of the acceleration was x minus x node, and actually we wrote it as s and s node. S minus s node is going to be equal to v node t 1 over a, the constant acceleration, multiplied by t squared. And since I have all the acceleration in the x direction, so I have x minus x node is going to be equal to v node x t plus half of the acceleration x t squared. I know that v node is equal to 0 because start at rest, and x node is equal to 0, and I know what is the distance, and the distance is 20. And this 20 is going to be equal to half multiplied by ax that I don't know, and I have t squared 2.58 squared. So this is going to give you that ax is equal to negative, by the way, this is not going to be negative because here I assume the x direction is going up, and here I assume the x direction is going down. So if you guys calculate this, I have the 20 is going down. By the way, so that you can understand what I did here. What I did here, I put x going up, so I put the distance in negative 20. Okay? Right now I did x in the same direction of the distance, so I put it here positive. So this value is going to be 6.09 meter per second square, and it's positive. Okay? All right, so let's substitute in this equation. So I have negative the normal force you guys just got it, 751.49 multiplied by the mu, the friction, and then plus mg, the mass is 100, the g is 9.81 multiplied by sine 40. All this should be equal to the mass is 100, and I just got the acceleration is 6.009. If you calculate all this, you will find that the friction coefficient is equal to 0.039, and I can write it like this. Okay? All right, let's see what did I do here. First, I did it step by step. Identify the body. The body is this here. And then I draw a free body diagram of the body. Free body and kinetic diagram. Laid out all the forces on this body, and I put the direction of the acceleration here. Don't mix the two things together, okay? Do this in a separate drawings. Free body diagram, you get 5 points. Kinetic diagram, you get 5 points. If you put them, all of them here, you lose 5 points. Okay, 2 of them alone. So all the forces in the x direction is gonna be equal to the max. And all the forces in the y direction is gonna be equal to the may. And that's what I put here, x and y. And then I start substituting with the forces, right? To find the components in the x direction and making them equal to ax. And the components in the y direction and making them equal to ay. And then I used some principles from what we learned over the last 2 weeks to get the acceleration. That's why I give you distance and time. All right, let's solve another problem just to confirm that we understand this concept. and I solved many problems here, so if you wanna expand your knowledge. Okay, so let's do it here. So this problem is saying a smooth 2 kilogram collar says there's collar here and it's moving on this bar up and down, but this collar is attached to a spring and this spring is fixed here. This is the initial position of the spring. It was something like here, but the final position of the spring was somewhere here at distance y. That's the spring. The spring has a stiffness K, and this K is 3 Newton per meter. Okay. And this spring was unstretched here. The spring here was unstretched. The distance was 0.75 meter. The unstretched length is 0.75 meter. If the collar is released from rest, here is the rest until cut distance y. Determine its acceleration and the normal force of the rod on the collar at the instance when y is equal to 1 meter. First, before I solve this problem, let me revise some concepts with you. Have you guys dealt with springs before in physics? So do you guys know what the force in the spring should be? Okay, like let's say I have a spring and I stretch this spring. This spring has stiffness 3 Newton per meter. And I stretch this spring 1 meter. What is the force inside the spring? Exactly, excellent. So basically, it's called a Hooke's law. Like if you have a spring, and this is the key of the spring, and you compress this spring delta here, and this spring became here, you compress it. The force F to compress this spring delta, F is equal to K multiplied by delta. Okay? The stiffness of the spring multiplied by the displacement that this spring did. If this spring unstretched, it doesn't have any forces. But the spring has internal forces once you compress it or you put it under tension. This force helps him to restore its original length back. Like let's say this spring unstretched length is 0.75. You compress this spring 0.25 meter. What is going to happen when you release the force? It's going to go back to unstretched length with a force F multiplied by delta. What if you extend it with 0.25? It's going to return back, okay? All right, so let me ask you, what is the force of the spring on this body here? Given that the unstretched length of the spring is 0.75 meter. Okay, the spring is unstretched at that location, so the forces from the spring is equal to 0. Because the spring is unstretched. When the spring is gonna act up on this body, when it's getting stretched, like this position. So if you wanna know the force on this body, you have to find L node of the spring and L final of the spring. L node of the spring is 0.75 meter. F final of the spring, can you guys find it? At y equal 1 meter? If you know that this is 0.75 and this is 1 meter, what is the L final of the spring?
1.25.
What? How did you know? So yeah, it's I saw that you just short numbered. So you got the hypotenuse, and this is equal to 0.75 squared plus 1 squared. This is 1.25. Did you guys calculate it? I don't know. Did it here? I left them all under the roots. But can you guys do this calculation? Tell me what the number exactly. 1.25? 1.25 meter. That's the L final. Okay, so I knew right now what is the L final, what is the L inert. So right now I can know what is the F spring equal to. Okay, how? By multiplying K by delta and K of the spring. I know it's a 3, and delta is L final minus L node, and this is going to be 3, 1.25 minus 0.75. So this is going to be 0.5 multiplied by 3 is going to be equal to 1.5 Newton. Right? This calculation is not, oh yeah, it's here. The PS is equal to 1.5. Alright, so I have it here, F spring. I got the reverse force. But this is not the only force that acts on this body. That's why I told you, before you do any calculation, you have to identify the body, and I know it's this body. And it's already given me that what is the mass of this body is 2 kilograms. I always give you the mass. And then I told you to draw a free body diagram. This is the body. This is for the free body diagram, and this is for the kinetic diagram. And I told you put all the forces here, and here map all the coordinate systems. Okay, so let's see what forces that we have on this body while it's moving. The spring, and the spring is at this location is something like this. This is F spring, and it has angle theta, and in a few minutes we're going to find out what is this angle theta is. All right, so this is the F spring. What is the second force? What other forces that act on this body? Weight. Before you do anything, weight is number one force. Any body has a weight. Okay, that's force number one, even before the spring. What other forces acting on this body? This body that way, with this force, is gonna leave the bar. The thing is, this bar have to, like, once you pull this that way, this bar has to have a force, normal force like this. Okay, acting perpendicular to the body. So there is always surfaces has bodies on our masses. Like, let's say you are trying to grab this out of my hand, but my hand is grabbing the other way. That's the same thing with the collar. Like, this is taking that way, my hand is taking that way, but rather than my hand, is this bar has a normal force on this so that it doesn't leave the bar. Okay? Alright, so this normal force is something like this, perpendicular to the surface. And that's all the forces on this body. How about the coordinate systems? You can put the coordinate system wherever you like. Like, if you want to put them up, you can put them up. If you want to put them down, you can put them down. Let's just stick with what I did here so that we can check the numbers. I put X that way, and I put Y that way. However, from my perspective, I can put Y down because I know that W is going down and the body is going down. I know for sure that the MA is down because this body will never go up. When you leave 2 kilograms, it's going to go down with the gravity. Okay, so MA is going down. Then I'm going to do the same thing that I did here. I'm going to do it in X direction and Y direction and try to figure out the variables that he's asking me for. So let's say number 1 in X direction. Sum of fx is going to be equal to max. You guys tell me, what is the acceleration in X direction? Does this body have any acceleration in X direction? All the acceleration, this body is going down. It didn't move any X direction.
I think the slides got it. Well, do you account for any friction?
Oh yeah, that's a good question. I believe here it says it's a smooth 2 kilogram puller. So once you hear it smooth, that means there's no friction. Okay, so that's the verse word in the problem. A smooth 2 kilogram puller. So this thing is a smooth. So there's no friction. If I didn't say smooth, you have to assume friction. Okay. So let's find theta first before I do anything. Can you guys tell me what is the value of theta? Okay, let's say what is the sine theta and what is the cosine theta? Well, I know this, right? So this we just calculated, it's the root of 0.75 squared plus 1 squared. .75 squared plus 1 squared. Okay, sine theta is going to be the opposite, which is 1. And cosine theta is going to be 0.75. Right, so I know what is the cosine, and I know here I'm going to have Fs cosine, and here I'm going to have Fs sine theta. Alright, can you guys tell me what should I write in the x direction? What are the forces in the x direction? Fs cosine theta minus n equal to 0. There are no other forces. Okay, F spring we just got it here, 1.5 Newton. We got the delta, which is L final minus L node, and multiplied by K, and we got the force in the spring. It's equal to 1.5. And cosine theta we just put it here, which is 0.75 over the root of 0.75 squared plus 1. You can calculate this value right away and substitute it here, but I would rather do it in the final equation because there was a lot of approximation here. So, and then I put minus the normal force is equal to 0, and then you can get the normal force, and that's the first ask in this problem. Find the normal force. The normal force here is equal to, after we do this calculation, it's going to be equal to 0.9. Alright, so I finished the x direction. Let's finish the fy direction. Sum of the forces in the fy direction is going to be equal to my, and that's the second ask. In this problem, I'm asking you to determine x acceleration and the normal force. I got the normal force. In the second, I want to get ay. So what is the forces in y direction? And pay attention to the positive or the negative. What is the forces in the y direction?
Weight.
The weight, is it positive or negative? And Fs sine theta, is it positive or negative? Positive. So I have Fs sine theta minus W is going to be equal to MAY. So Fs, we calculate is 1.5 multiplied by the sine theta, which is 1 over the root minus W. W, I have the mass 2. Never put 2 alone, multiplied by 9.81 to convert the mass to weight. And this is going to be equal to the mass, which is 2. Multiplied by AY. And that's it. That's a one equation, one variable, which is AY. And then you are going to find AY. But before I put AY, can you tell me, is AY is going to be more than the gravitational acceleration or less than the gravitational acceleration? Use your engineering sense. Assume you hold this body without the spring, and you leave it, and with a spring and leave it. Which one has more acceleration than one without spring and one with a spring? Without spring is going to go with more acceleration because the spring is holding you back. So this is definitely less acceleration than the gravity. So if you got this as a 10 or 11, that means that you have done something wrong. But if you got it like 9.2 meter per second squared, yeah, that makes sense because it's less than the gravitational acceleration. But if you got this 20, you have to think, it's 9.81, that's my free fall. And I'm holding it with a spring, that means it's not a free fall, okay? And let me ask you, if this is spring not 3 Newton per meter, if it's become 30 Newton per meter, is this number is gonna get bigger or less. This number, the spring stiffness, becomes 30 or 300. This number is gonna get bigger or less. Smaller. Why? Because it's more stiffness. That means, like, let's say this stiffness is infinity. Like the stiffness of this spring is infinity. Very stiff rock, doesn't extend. That means this body has acceleration 0. Because it's not gonna move. But once this body is having a stiffness and extend, that means this body can move up and down. And if this stiffness is 0, what is the acceleration? The maximum acceleration that we can get here? 9.81, the gravitational acceleration, is going to do a threefold. If this spring has a stiffness of 0, or you cut this spring, this body is going to do a threefold. So you are bounded by the gravitational acceleration here. It's never going to get more than 9.81 if you just leave it. And if you increase the stiffness of this spring, this acceleration is going to get lower. That's why you have to use your engineering sense while you are solving the problems. All right, see you guys next time. We're going to do application on tangent normal next time, and I believe there's some solved problem in the textbooks and also the notes. You have quiz next time on the curved linear motion and the independent motion. This is just like joint campus.
How you get it on the camera.
Wait, I'm gonna wait for him too.